Hello everyone. Today we will explore a fundamental topic in physics and engineering, momentum and collisions. This concept helps us understand how objects move and interact in the real world, from car accidents and sports to rocket motion and robotics. Essentially, momentum depends on an object's mass and velocity. In this presentation, we will look at different types of collisions and, most importantly, how the law of conservation of momentum works in practice. Definition and formula of momentum. Momentum is an important concept in physics that describes the quantity of motion an object has while moving. It is defined as the product of the mass of an object and its velocity. This means that both the weight of that object and the speed at which it moves affect its momentum. An object with a large mass moving slowly can have the same momentum as a small object moving very fast. Momentum is considered a vector quantity because it has both magnitude and direction, and the direction of the momentum is always the same as the direction of the object's motion. In this equation, P represents momentum, M stands for mass, and V represents velocity. The SI unit for momentum is kilogram meter per second. Momentum is very important in understanding how objects behave during motion and collisions. For example, a fast-moving car has a large momentum which makes it more difficult to stop quickly. The law of conservation of momentum states that the total momentum of a closed system remains constant unless an external force acts on it. This principle is widely used in many fields such as engineering, transportation, sports, and space science to analyze motion and predict outcomes of collisions and interactions between objects. Conservation of momentum. We start with Newton's third law, which states that for every action there is an equal and opposite reaction. Therefore, the force exerted by object 1 on object 2 is equal and opposite to the force exerted by object 2 on object 1. And here we have Newton's second law. We define momentum as the product of an object's mass and its velocity, represented by the equation Next, we substitute Newton's second law in terms of momentum, replacing each force with its respective rate of change of momentum over the time interval. And since the collisions occurs over the exact same time interval for both objects, the time term cancel out from both sides. By expanding the brackets and arranging the terms to separate the initial and final states, we arrive at our final conclusion. The total initial momentum before the collisions equals the total final momentum after the collisions. This clearly proves the law of conservation of momentum. And as you can see, this is an example for what we spoke. Types of collisions. Perfectly elastic collision. The idea, objects bounce back like a perfect spring without changing shape or losing any energy to heat or sound. Example, billiards. Due to their rigid material, the balls do not deform upon impact. Instead, kinetic energy is fully transferred from the first ball to the second. The cue ball stops completely, and the second ball moves at the original speed. In elastic collision, the idea, objects undergo plastic deformation. A portion of the kinetic energy is permanently lost, dissipation as heat or sound, or consumed by internal deformation. The result, the post-collision velocity is always less than the approach velocity, which mathematically explains why the coefficient of restitution is fraction between 0 and 1. Completely inelastic collision. The idea, The extreme state of kinetic energy loss where objects completely lose elasticity. Instead of bouncing, they deform or overlap, sticking together to move as a single common velocity. A bullet penetrating and stopping inside a block of wood due to friction, forcing both to move together as a single combined mass. Linear vs angular momentum. Understanding the difference is essential for analyzing different types of motion. Feature: linear momentum. Motion type: straight line. Formula: P equals m multiplied by v, main factor, mass and velocity. Practical applications of momentum. Automotive safety, using a crumble zones and airbags to increase the impact time, which reduces the force exerted on passengers during a crash. Rocket propulsion, based on the conservation of momentum, ejecting gas backwards at a high speed gives the rocket an equal and opposite momentum forward. Sports. In sports like tennis or basketball, players follow through to increase the contact time between their equipment and the ball, maximizing the force transfer. Billiards. Collisions between billiards balls demonstrate the transfer of momentum, allowing for predictable motion and game strategy. Now let's take a look at a practical example to see how the laws of momentum and collisions works in reality. Imagine we have two carts, both weighing 2 kilograms. The first cart is moving at 4 meters per second, whilst the second one is completely stationary. When they collide, they stick together, which gives us what we call a perfectly inelastic collision. By applying the law of conservation of momentum, we can easily calculate the final velocity. As you can see from the formula on the slide, since the second cart wasn't moving initially, its momentum is zero. This simplifies our calculations, relieving that the combined system moves forward at a final velocity of 2 meters per second. But here is the most interesting part. If we calculate the kinetic energy before and after the crash, we notice a significant change. We start with 16 joules of energy, but end up with only 8 joules. Where did the rest go? Exactly half of the energy was lost, converted into heat and sound during the impact. This perfectly illustrates our main point today. Whilst momentum is always conserved in a closed system, kinetic energy is not necessarily preserved. To conclude, we have seen today that momentum and collisions are not just equations on a whiteboard. They are the governing laws behind critical real-world applications, from car safety and space exploration to robotics. Understanding these principles gives engineers the vital power to predict, innovate, and ultimately build a safer, more efficient future. Thank you.